Okay, we're going over chemical bonding 2, and chemical bonding 2 picks up where we left in the other chapter, chemical bonding 1. So we're going over other aspects of bonding. So with chemical bonding 2, if you're going to take organic chemistry, you will see chemical bonding 2 over again. What chemical bonding 2 gives us is more insight about covalent and ionic bonding that we were not able to get from Lewis's theory and the Vesper theory or the Vesper model. Okay, so with this part here in this section, we're going to be talking about two major theories that will be valence bond theory and then molecular orbital theory. Okay, so we'll start with this and then we'll go into this. But before we start into the valence bond theory, an observation was made in the lab that led to the discovery of this theory, which is a magnetic property in liquid oxygen. Okay, now reading the title alone, we're thinking, wait a minute, liquid oxygen. Oxygen is a nonmetal, right? So as a nonmetal, how do you expect to have magnetic property? Okay, so magnetic property in a nonmetal? Very unexpected, right? Okay, so it's usually something unexpected that leads to investigation then leads to discovery, and then the rest of it is history. So liquefied oxygen is a paramagnetic. Okay, and so we'll see how it's a paramagnetic. We've talked about paramagnetic before, but we've seen this behavior where you had the partially filled orbitals. We've seen this behavior in elements. Now we're talking about the oxygen molecule. Paramagnetic means attracted to a magnet. So in paramagnetic elements or molecules, they generate their own magnetic field that is then influenced by an external magnetic field. So they become magnetic, so to say. Paramagnetic materials has unpaired electrons. So neither Lewis's theory nor the valence bond theory or the Vesper theory explains that. So when we get to the molecular orbital theory, we will actually be able to finally explain what's happening with liquefied oxygen. So even as we're heading into the valence bond theory is still unable to explain the observation. Why do you have a nonmetal having a metallic property while it's still a nonmetal? Okay. So here's the observation right here. What appears as water here is technically liquefied oxygen. And so oxygen is pressurized and converted into a liquid. And then these are two ends of a magnet. So these are magnets. And as you can see here, the magnets trap the liquefied oxygen, preventing it from pouring. So it hasn't really changed here yet into a gas state, but it's in the process of changing from a liquid to a gas state. But in the process, it gets trapped between the two ends of the magnet. Okay. So they're showing you here the unpaired electrons responding to the magnet, and they're being oriented in one direction versus the other. Anyway, so we now move into the valence bond theory, talking about orbital overlap, which then results in the chemical bond. So before we go into this, I want to do a quick recap. Okay, kind of like a compare and contrast. When we were talking about covalent bonds, so our discussion today will be mostly covalent bonds. We previously said we make covalent bonds by sharing electrons. And of course, sharing electrons, this was Lewis's point of view of bonding. Bonding happens when we have sharing electrons. So I'm going to show you two hydrogen atoms combining to form a hydrogen molecule. So one hydrogen will come in with one unpaired electron. According to Lewis, the unpaired electron is a dot. The other hydrogen will come in with an unpaired electron, also a dot. When these two combine to form a molecule, each hydrogen will bring its unpaired electron. They will share, and as they share these unpaired electrons, the unpaired electrons translate into the shared unpaired electrons translate into a bond. And this is Lewis's version of covalent bonding, okay, where we see the sharing of unpaired electrons. So sharing is essentially bonding, right? Sharing unpaired electrons. Okay, so what is valence bond theory's version of a chemical bond, the same covalent bond? What they're saying here is when you apply quantum mechanics to molecules, the bonds between atoms should occur when the orbitals on those atoms interact to make a bond. So we're trying to talk about the same bonding, covalent bonding, from the point of view of quantum. So in quantum, we focus more on the electron in its home, or the electron in its orbital. So they're talking about the orbitals. Of course, they mean the electrons, right? But the electrons do not leave their orbitals. So for the electron to bond, the orbital must interact. The kind of interaction depends on whether the orbitals align along the axis between the nuclei or outside the nucleus. So we're going to be examining bonding in this picture. And this story starts from the right to the left. Essentially, we're looking at two hydrogens here that are about to form a bond. So we see the interaction energy of two hydrogen atoms. So it starts right here. This is a hydrogen, and this is the other hydrogen, and their goal is to form a bond. So according to valence bond theory, if these hydrogens are about to form a bond, we know the hydrogen does have, each hydrogen has an unpaired electron, right? And the unpaired electron is not shown in this picture, but it will be shown later on. And according to the quantum theory, unpaired electrons are shown as arrows. So remember, this is the same story from the point of view of valence bond theory or quantum theory. So they're shown as half arrows. So we can say one of the hydrogens has a half arrow pointing down, the other one has a half arrow pointing up. Okay, the arrows are not shown in this picture, but you can imagine they're here, and this one is here. And so these electrons are about to form a covalent bond, right, from each hydrogen. Okay, so the hydrogens start off at a distance apart. And by the way, as we are tracing the energy caused by their interaction, please notice the lowest energy usually indicates stability. So lowest energy equal stability. Okay, but not only that, the human interpretation of low energy is also preference. So we assume that elements prefer to be at a state of low energy, compounds prefer to be at a state of low energy. So when we see stability or low energy, we also interpret that as a preference. That means the elements prefer, preference. If I can spell this, can I write and talk and spell? Stability, and then also a preference. Okay, so here you have the two interacting orbitals at a certain distance apart. The energy is close to zero, so it's kind of high compared to the lowest point, right? As they get closer and the electrons, the unpaired electrons move closer, the energy level decreases. And then when they get to a point, this is a point where they're close enough to form a bond, right? So at this distance, they're forming a bond. They tend to have the lowest energy. So this is the bonding energy. Therefore, each atom is at a bonding distance from the other. And then there is such a thing as too close, right? People say you can't be too close in a relationship. Apparently, according to valence bond theory, you can be too close. So here you have the same orbitals interacting in a distance that's too close, closer than the bond energy distance. And so when you have that situation here, the energy gets very, very high, right? It's actually higher than the energy each orbital had before they started to bond. Okay, so this is destabilizing, this is stabilizing, and of course, this is in the process to become stable. So, two elements will prefer to be in a bond. How do we know that? When they're bonded, lowest energy ever, and they're stable. So we communicate that or interpret that as satisfaction. Okay, so then we're moving on. So after seeing that illustration, we're going to summarize valence bond theory. In valence bond theory, the valence electrons of the atoms in the molecule reside in quantum mechanical atomic orbitals. So just like I was able to show you bonding here, I'm going to show you bonding again from the point of view of valence bond theory. So of course, by saying valence bond, this is referring to the electrons that are bonding. So it's valence electrons that bond, right? And they bond, of course, we're talking about covalent bond. Covalent. I can't spell today. This is what happens when you stay up late. Covalent bond, right? The valence electrons are participating in a covalent bond. So I'm going to be showing the hydrogen on the left. Here is my one electron, the hydrogen on the right. Here is my other electron. Now I show the electrons being opposite spins. There's some books that start with both electrons having the same spin, okay? But in order for these electrons to even, or for the orbitals to overlap, and for the electrons to occupy a similar space, they have to end up on opposite spins. So even if a book starts with the electrons being on the same spin like this, when they're about to bond, they have to end up on opposite spins. So one has to be up spin, the other one has to be down spin. So here we have our two hydrogens. And then when you have the overlap of orbitals, then we have bonding. So in this case here, in like a weird sci-fi move, these electrons participate in a bond without ever leaving their home. Okay, so this was probably hard to explain years ago because, when it comes to Lewis's theory in bonding, the electrons appear to move, right? They appear to move in his illustration. They move, or they kind of come close and they're shared. Here is happening, only we're seeing what is happening with the orbital, right? The orbitals are not necessarily moving. The electrons remain in their respective orbitals while the orbitals overlap. So without overlapping orbitals, you do not have bonding. Here, you do have overlapping orbitals, and when that happens, you have bonding. So this is essentially covalent bonds. Okay? So the atomic orbital we see that's been used here to form the covalent bond based on its shape, this is going to be the 1s, and then of course the 1s from either hydrogen. So we're getting into all that. The orbitals can be the standard s, p, d, or f. Remember we had these before, where the s was spherical, the generic shape, p was figure 8, d was the clover leaf, and then f was the flower. Okay, it's a little bit more complex than that, but remember, right? You have 1 circle, 2 circles, 4 circles, and then 8 circles. It's hard to draw the flower. But yeah, when you are interacting orbitals, when you are overlapping orbitals, you can use the basic standard orbitals we talked about before, the SPDF, or you can use the hybrid combination of these orbitals. So we'll see how we make hybrids of the orbitals. A chemical bond results from the overlap of two half-filled orbitals. If the orbitals are both empty and you overlap them, you do not form a bond. In this section here, to form a bond, there are two requirements. You have to have orbitals overlap, and then when they overlap, they have to somehow overlap so that the overlapped area contains two electrons. So you have to have overlapping orbitals and then end up with two electrons. And we're told here the electrons have to be spin paired. Spin pairing of the two valence electrons is required too. So I guess that's a third requirement, right? When the electrons are in the overlap region, they have to have opposite spins, even though technically they're not in the same orbital, but they're in the same region and they're forming a bond. And this is a requirement, a prerequisite of the bond. Okay. So the easiest way to form a bond is by overlapping two half-filled orbital, or let's say here, or the less commonly commonly the overlap of completely filled orbital with an empty orbital. And in this case here, it's saying one orbital can be completely filled while the other one can be empty. And when these two overlap, they end up in the same scenario right here. Okay. And this usually happens with the last hydrogen in NH4 plus. So to quickly illustrate that, what this is saying is when you are making NH4 plus, wait, why do I have all this drawing here? Oh, right here. When you have NH3, ammonia right here, you can see this is the regular bonding we're used to. To make NH4 plus, you're bringing in the last hydrogen, but the last hydrogen comes in after it's lost its electrons. It has 0 electrons. So when the hydrogen comes in here, this nitrogen has its lone pairs right here. The hydrogen comes in with its empty orbitals and overlaps with this. So in the end, as far as quantum is concerned, the overlap region has up and down, but we all understand nitrogen provided the bonded electrons, not hydrogen. Hydrogen came in with an empty orbital. Okay. And then once we have all this overlapping, what happens? We then go back to geometry. The geometry of the overlapping orbitals determines the shape of the molecule. So we'll get a chance to revisit the shapes of the molecule according to that table. Okay. So now we're looking at bonding. For us to look at bonding, the orbital diagram for H2S. We're going to look at bonding once again. Even though we're learning about valence bond theory, we have to go back and look at Lewis, okay? So we can see what led to valence bond theory. This is showing you how bonding takes place from the point of view of the orbital diagrams. So with Lewis's structure, and when I was a student, instead of learning scaffolding or building schema, I think scaffolding sounds more sophisticated. When you're building new knowledge on the knowledge you already have, okay? So I like to use the knowledge I already acquired as an anchor to help me navigate into the unknown or what felt like the unknown. So on the left, I will draw the Lewis structure so I can help you if you need that. We're going to draw the Lewis structure of H2S. And so the Lewis structure throughout the rest of this chapter will help us to anchor our valence bond theory models and then our molecular orbital theory models. Okay, so Lewis structure for this, we know how to draw that. Let's see, sulfur is in group 6 and we only have 1 in the structure, so that gives us 6 electrons. Hydrogen is in group 1 and we have 2 in the formula, and so we have 2 here, 8. Right? So as far as my Lewis structure is concerned, I have sulfur in the middle. I have hydrogen on either end. Single bond, single bond. Let's see. 2 bonds, 2 bonds, 4 electrons minus 4. I'm left with 4 electrons. I put 2 up here, 2 down here, minus 4. I'm left with 0. So my Lewis structure is here on the left. Let me draw this in the bottom right here. And this will be my anchor. Okay, so in my Lewis structure, I can see I have 2 bonded electrons around sulfur, 2 lone pairs electrons around sulfur. Now let's see this same illustration, but from the point of view of orbital diagrams. And the orbital diagrams will ultimately lead to the valence bond theory model. Okay. Okay, in the orbital diagram, the central atom is sulfur, right? So you want to draw the orbital diagram for sulfur. So what is sulfur again? Orbital diagram, to draw that, we need you can use the valence electrons or you can use the whole configuration. So I'm going to shorten this and say sulfur has what, 16 electrons? So its shorthand configuration is neon, right, in brackets. And then after neon, I have 3s2, 3p, 1, 2, 3, 4, 4. Okay, so this is a shorthand configuration. From this configuration, I can draw my orbital diagram, right? I'm going to draw it for this and for this. Okay, so for sulfur, that has 16 electrons, my orbital diagram, remember for S, this is 3s2. S usually has 1 orbital. For the S sublevel, we have 1 orbital. For the P sublevel, we have 3 orbitals. So I got 1, 2, 3. Okay, so S sublevel, one orbital, I place both electrons here, up, down. P sublevel, I have three orbitals. I have four electrons to place, up, 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 down. Okay, so after I draw my orbital diagram, from this, what I get is I notice the number of unpaired electrons. And we see here, number of unpaired electrons equal covalent bonds. So somehow there's a correlation between the number of unpaired electrons and the number of covalent bonds that can form. So I can predict right here, based on sulfur being the central atom, if sulfur is going to form a bond with hydrogen, it can form two covalent bonds, right? This is without me drawing the Lewis structure. The Lewis structure is going to confirm what I'm seeing here. Okay, so I know that each hydrogen can bring in one electron, right? So what I'm going to do here in this structure to finish it up is where I have unpaired electrons or electrons with no roommates, I'm going to bring in the hydrogen electrons. So one hydrogen can park right here, the next hydrogen can park right here. And using the orbital diagram, I have really illustrated where these hydrogens actually go to bond. Okay? Sulfur can host a maximum of two hydrogens, and the two hydrogens, each of them pairs with the unpaired electron available around sulfur. And so from here, then, I can draw my valence bond theory model, which, let's see, do they have it right here? They have it right here. So in your valence bond theory model right here, I won't even try to draw this one because it's kind of complicated. It shows you of the orbitals available, two are used for bonding. And you can kind of look over here, right, and say which ones are bonding. So I'm going to highlight the yellow ones to be the bonding ones. These two here are used for bonding, right? Sulfur uses them to bond with hydrogen. Let me use a different color. Let's say green. These here, these orbitals are used for lone pair electrons. I said I won't try to draw this because it's complex. The lone pair electrons, there is one lone pair electron, this one here, this pair, that's part of the p orbital. The other lone pair electron is part of the s orbital. So they try to draw that in the picture. I will not even attempt to draw it. Now I will recognize it, okay? In this picture here, it may be hard for you to see, but this is a huge p orbital, right? This here is a huge p orbital. And then the one that goes in and out, at least it looks like in and out to me, is a huge p orbital. Okay? So we have three p orbitals. One of the p orbitals is used for a lone pair. The other two are used for bonding. So I'll say this is B for bonding. This is B for bonding. Okay? And then around, these are all, remember, around the sulfur. And then apparently the sulfur also has the s orbital right here. That's why I said it's complex, where there is a lone pair. So s orbital, and there's a lone pair there. So all I'm doing is interpreting this picture, right? Remember the two p orbitals were used for bonding? This picture here is showing you how bonding is taking place. Hydrogen came in with this round orbital, right? 1s, overlapped with one of the p's, and formed a bond here. The other hydrogen came and overlapped with the other p and formed a bond here. So here's where we have a bond, and here's where we have a bond, okay? You don't have, if I'm not drawing this, you don't have to draw this particular structure. What you want to know how to draw is the easier ones, and I'll walk you through that part. Okay, so this is a summary of what we saw again, so I'm not going to go over this again. So exactly how are we bonding here? Let me use a brighter color. According to the valence bond theory, bonding takes place between atoms when their atomic or hybrid orbitals interact. Interact here means they overlap. You have to have the orbitals overlapping, right? They can be atomic, meaning S, P, D, F, or they can be hybrid, and I'll show you what these are. To interact, the orbitals must do either one of the following. They have to either be aligned along the axis between the atoms or be parallel to each other and perpendicular to the interatomic axis. So these words, which I don't like the way the slides were lined up here. But we will explain what this means when we get to. Let me explain it right now. When we get to the bottom, at some point they talk about what that means. Okay, there are two different ways in which orbitals interact. Okay, and it's hard for us to really see this in s orbitals. This is easier seen in p orbitals because p orbitals actually look different depending on how you're looking at them, like where you're standing relative to the orbital. So in the first one, it says be aligned along the axis between the atoms. With that one here, let's say this is the axis, and then like the x-axis, right? And then you have two px's. So px on the left and a px on the right. Px, px. And these px's lie on the x-axis. And these two are about to interact. If they're about to interact, remember, the lobe has to overlap. So to overlap them, hold on, this is a little tricky to draw. Okay, hold on. There. They overlap as they still remain on that axis, okay? So here you'd have your electrons in there. You may have your unpaired electrons here. When you overlap them, you end up with that. So these are overlapping along their axis. And it says here, they're pretty much lying on the axis as they overlap. And later on, we'll see that orbitals that overlap while still lying along the axis like that, this type of overlap will be called sigma. And so this symbol here that looks like a 6 with a squiggly top is called the sigma bond. Okay, so I covered this in general chemistry when I was a student, but I was accountable for it even more in organic chemistry. So what I'll do is I'll hold my hand, like I'll raise my hand, both my left and my right hand. So it was I guess horizontal to the floor, and I'll hold each hand to the other, like, kind of like shake hands, my left and right hand, and that will illustrate a sigma bond. And I'll have my hands, at the side of my face, kind of like doing the Vogue movement with Madonna, and that will be my vertical bonds, right? In that case, my pi bonds, my overlap, that's side by side. So when you have orbitals that are parallel to each other, but they are perpendicular to the interatomic axis. So let's stick with this axis being this way. This time our orbitals are up and down to that axis. So this could be a py or pz, any orbital that is not a px, because the px's tend to lie along the x-axis, right? So here we're dealing with, say, py or pz. So if these are coming together to overlap, oh, by the way, py and py can overlap. Py doesn't usually overlap with pz. Okay, so they stick with their kind as far as the orbitals are concerned. Okay, py will overlap with py because of the orientation. So py overlaps with py like that. They're both vertical in this case here. So when they're overlapping, I don't have space. I don't want to draw this over again. So I'm just going to bring it close together if I can, right here, like that. They overlap side by side. Now, because this is complicated, they usually kind of show it like this. And then they show the overlap like it's some kind of stream overlap like that. But realistically, they're actually literally overlapping like that, overlapping lobes. Okay, so side by side overlap, this forms the pi bond. And of course, pi has that symbol pi, like 3.14 pi, that symbol right there. So sigma bond, pi bond. So we'll talk about this down the road. Anyway, so when it comes to valence bond theory and the hybridization, we're finally getting into hybridization, right? One of the issues that arises is that the number of partially filled or empty atomic orbitals does not always predict the number of bonds. We just saw earlier from sulfur that if we counted the number of unfilled or unpaired orbitals, we could predict and say if you have two unpaired orbitals, you have two bonds. But that isn't always the case. That's what this bullet point is saying right here. Carbon, for example, if you draw its orbital diagram, carbon shows you that there are two unpaired electrons right here. This is unpaired, this is unpaired. And from looking at carbon's orbital diagram, you get the feeling that carbon will form two bonds. Yet in nature and even in synthetic compounds, there is no carbon atom out there that forms two bonds. So looking at carbon's orbital diagram, you would predict two or maybe three bonds that are 90 degrees apart. In reality, there is no bonds like that from carbon. Carbon actually forms four bonds, and the bond angle is usually 109.5 degrees apart. I always want to say FM so bad because that's how I survived learning this. Anyway, so how do you adjust for the inconsistency in the observation? There is a gap between the theory and the observation. Okay, you have to come up with another hypothesis, right? So it was postulated, right, that the valence atomic orbitals could do something to supplement for the lack of enough unpaired electrons. What they do? They could hybridize. So this is the rationale that scientists came up with. Like, okay, explain why carbon forms four bonds. Yet when you draw the orbital diagram, it only has two unpaired electrons. We suggest that it hybridizes. What is hybridizing? Okay, so right before it forms a bond, carbon is able to hybridize its orbitals as needed. Okay, does it sound to you like they're making it up as they go? Y'all, science is all about hypothesizing, right? And testing your hypothesis to see if it fits. If it doesn't fit, you change it. So one hybridization of carbon is to mix all two S's and all two P's to get four orbitals that point at the corners of the tetrahedron. Why are they suggesting hybridization takes place? This is very important right here. They're saying carbon, if you look at carbon without saying it hybridizes, then you will predict that carbon forms single bonds with two other atoms, like CH2. CH2 does not exist, but we have CH4. So carbon in reality has more bonding power than the theory we currently have suggests. So the purpose of hybridization in the central atom is just to increase its bonding capacity. It's to explain why it can form more bonds than what we expect. Okay, so we hybridize to form more bonds, and that's the bottom line of this. Okay, so does hybridization happen all the time? No. Hybridization only happens if a greater bonding capacity than the theory suggests is required. If the central atom, which I see the central atom to be a host, if the central atom has to form many bonds that we know it should be able to form, then we rationalize and say, oh, it hybridized. Okay, it's operating above its level, right? So yeah, it's operating above its level. So the level is essentially the rationale there is hybridized. Okay, so right here, what we're seeing is based on what it says here, this is the orbital diagram for the one hydrogen, right? One hydrogen pretty much has one S, one electron configuration, and then this is the one for carbon. Remember with carbon, what they're missing here is helium in brackets. So carbon has a total of 6 electrons, right? 6 electrons. So the first two are held by helium. The last four are held in the 2s. We have 2. The 2p, we also have 2. So remember the 2 sublevel, we always have one orbital. 2p sublevel. So 2s, one orbital, 2p sublevel, 3 orbitals, and you place your electrons in there. The 2s, we end up with up and down as we write the electron. 2p, we have up and up. Remember, you have to have filled the empty orbitals first before you go back and double them. Okay, so here's where we are right now. Now, we said earlier that if you go by the number of unpaired electrons, you will conclude carbon should have 2 bonds, right? If hydrogen is trying to form a bond with carbon, you see where you have your number of unpaired electrons? Yeah, that rule works for hydrogen. Hydrogen usually has one bond. Number of unpaired electron matches the number of bonds. But in the case of carbon, it doesn't work because in the end, this molecule doesn't work. It only works in theory when you're writing it down and you're saying it. But in reality, this is the carbon at the formula we see between the carbon and the hydrogen. You have the carbon in the middle. It does form four bonds. These bonds are not planar, they're actually 3D, and the bond angle is 109.5. There is no bond angle of 90 between the carbon and the hydrogens. Okay, the bond angle is 109.5, indicating 3D, versus this one here being 2D. This doesn't exist. Okay, so scientists said this here doesn't explain why this structure exists. So for that reason, we have to hybridize. So how do we hybridize? So what I'm going to do here is I'm going to show you how we get these hybridizing patterns. Okay, so I'm going to do a quick detour right here, because when I learned this in general chemistry, I want to say when I learned, when I was introduced to this in general chemistry, I think I got to understand it more in organic chemistry, because I felt like it was glossed over and I was supposed to remember it, and then I just kind of crammed it. Anyway, then I got to organic chemistry. I'm like, oh no, here it is again, and I have to remember it better this time. Yeah. So let's go back to the orbital diagram, right? In the orbital diagram, when we're dealing with S's, we usually just have one S, right? For S, we have one block, one orbital. For P's, we have three orbitals, right? So we're getting a chance to revisit quantum, right? For D, we have five orbitals. 2, 3, 4, 5. Okay. So we are trying to combine the orbitals in order to increase bonding capacity. So I'll say this. Remember, for S, we only had one type of S, so all we have is the S. For P, I'll say we had PX, PY, PZ. For D, there were 5 different D orbitals, right? I won't even label them. But what I'm going to tell you right now is, when we are done with all of this, we will match our orbitals to the number of electron groups. So I'll say here, the maximum electron groups is equal to 6. Remember how that little table I gave you, well, it was anything but a little table. The maximum electron groups that we have so far is 6. So the number of orbitals we need to mix will be a maximum of 6. Okay, so we'll start in this order. We will use this first. This will be our first. This will be our second. This will be our third. This will be our fourth. This will be our fifth. This would be our sixth. And then we don't usually use these. Okay, so what I mean by that, the maximum number of electron groups is 6. When we're trying to mix, we start with, let me write it right here, 1s and then 1p. 1s, 2p's. I should write this a little smaller, like I have a lot of space. 1s, 1p. 1s, 2p's. 1s, 3p's. These are the different combinations we can have. And then, so if you have 2 groups, you have sp. If you have 3 groups, you have sp2. If you have 4 groups, this is sp3. And this is for 2 groups. I should have written this somewhere better. We'll summarize this in the end. This is 3 groups, and this is 4 groups, right? And then if you have 5 groups, you have S plus P plus P plus P. So you take this S, you take this P, P, P. Now we have the 4 groups, right? We need one more orbital. We use this one here. So then plus D. And we end up with sp3d, 5 groups. Then, if we're trying to get 6 groups around the central atom, we use the S, so use up all of this. We use the 3 P's, this, P, P, P. And then let's see, this is the fourth group right now. We need to go all the way to six. We use the fifth one, the sixth one, D, D. When you consolidate, you get sp3d2. This is when you have five groups. This is a shorthand, sorry, six groups. This is a shorthand way of remembering this. The hybridization that, or the orbitals that the central atom uses to form the hybridization as needed. It all depends on the number of groups. Now, I have shorthanded this to kind of give you a quick way, a summary way to figure out what hybridization pattern will take place. Okay, what orbitals were mixed. So essentially, these are the orbitals, the ingredients, right? Orbitals mixed to make the hybrids. Okay, it all depends on the number of electron groups around the central atom. So I'll go over this again when we're actually applying it to solve problems. Okay, so they talk about this here. Some atoms hybridize their orbitals to maximize bonding. More bonds, more full orbitals, more stability. There we see it again. It's all about stability, right? When it comes to us humans, right, and stuff is happening, why is the government doing A? You know how it is. It's all about money, making money, making money. Why are they doing B? It's all about money. Why is our institution doing A? It's all about money, right? So with people, it's all about sometimes when we make judgments about people, why are they doing what they're doing? You know it's about money, or you know that they want to be happy. It's about being happy. So with the elements, most of the rationale behind their behavior, elements or compounds, it's about stability. Okay, so hybridizing is mixing different types of orbitals, like you saw, right? All the orbitals have s, so it starts in order. We always go through s, then p, then d, so don't skip. Okay, all the orbitals, the hybrid orbitals, have s, and all the hybrid orbitals have p, and then some of them have d, depending on how many groups you have. Yeah, so you're mixing different types of orbitals in the valence shell to make a new set of degenerate orbitals. Remember degenerate. These terms are coming back because we're going back to the world of quantum. It's like a little community where certain words are used only in that community. Degenerate means equal energy, new set of equal energy. The same type of atom can have different types of hybridization because it's showing you here carbon can do sp2, sp2, sp3, depending on what it is bonding with and depending on how many of those atoms it is bonding with. Carbon would choose to hybridize to generate the number of bonds needed. Okay, so it doesn't always hybridize the same way all the time. So we're told the number of standard atomic orbitals combined equal the number of hybrid orbitals formed. So actually, this is an important statement to hear, not to say the other ones are not important, but I'm just telling you this is an important statement here. So what I mean by that is, I didn't add this because I don't want to unfold too much too soon. If you're taking one s orbital and adding it to one p orbital, you're essentially adding two orbitals to each other. And your goal is to make a hybrid orbital. You're going to end up making two sp orbitals. I mean, you're going to make an sp orbital and another sp orbital. That is what this is saying. The number of standard atomic orbitals combined equal the number of hybrid orbitals formed. Not just the type, but also the number. Okay? And with the other one, if you added one s plus two p's, in other words, one p and then one p like that, since you added three regular orbitals, you will end up with sp2, sp2, sp2. Since you added three here, you have to end up with three here. Okay, so I'm trying to unfold a little as we go along the way versus just dumping it all right there. Okay, it's the same thing. I'll do one last one. If you're making one s and one p and one p and one p, since you're adding a total of four regular orbitals, you're going to end up with four of these other ones. So you end up with sp3, 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 sp3. So versus memorizing this, which for me, memorizing is a challenge. I'll show you when you're working this out how it actually does work out so that you're recognizing that you are making four of these. Okay. So they gave you the example here. I already showed you hydrogen cannot hybridize. Hydrogen, when we're going to be doing all this, hydrogen cannot hybridize for many reasons. And that's why hydrogen is not the central atom. We need the central atom to have the ability to host as many surrounding elements as necessary. Hydrogen only has one electron in its valence shell, and hydrogen only has that one electron in that one orbital. So when you mix up one orbital with something else, it doesn't have any more electrons to spread around. So hydrogen cannot hybridize. It is not central atom. Okay. So in a way, it doesn't have the responsibility of hybridizing. Only the central atom has to act as a host. So here we're finally seeing the hybridization work out. So we're seeing carbon here as it forms sp3 hybrid orbitals. So I'm going to draw this out so we can see how it works out. So this is the part where you want to be able, you want to know how to do this, starting with this. Okay, as far as illustrating the hybrid orbitals. So I'll start with the unhybridized. So for this picture to work, mine will not be as good as theirs because they're using computers. Okay, that's my excuse. Remember, the energy level goes from lower to higher energy level. So we have a lower energy level on the bottom, and then we have a higher energy on the top. Okay, so whatever is drawn on the bottom is assumed to have lower energy, like this blue 2s. Then whatever is drawn on top has a higher energy, like the red 2p. And then, of course, once you make the hybridized orbitals, they use colors here to illustrate mixing. So you would have to know that if you mix blue and red, you get purple. So what you're saying is that it's kind of like, to me, I think about cooking, that you're taking a certain amount of blue, mixing it with red, and it's not spotty. There's an even mix here. So if you have four of the regular standard orbitals, you end up with four of the hybrid orbitals. So you see 1, 2, 3, 4, right? You end up with four of these. Okay, let's go ahead and illustrate our own here. We'll have our standard orbitals on the left, and then we'll have our hybrid on the right. And of course, we're showing this for carbon, right? Doing the same thing that they're doing. Remember, it goes from lower energy to higher energy. So for carbon, remember, where do I write this? The configuration for carbon is shorthand. Carbon has 6 electrons. So we have what? Helium that takes care of 2 electrons. After helium, I need to have my periodic table here because I'm doing so much. My brain is like overload. Okay, helium has 2 electrons, then we have 2s, and then the electron 3 and 4 go over here, and then 2p, electron 5 and 6 go here. Okay, so electron 1 and 2 are with helium, electron 3 and 4 are at the 2s level, electron 5 and 6 are the 2p level. Okay, so remember, it's Aufbau, right? Aufbau is a scientist who talked about the different levels in the sublevel, starting from the lower energy level to the higher. He said that essentially 2s will be lower in energy than 2p. Remember, p's have to be 3 orbitals. 1, 2, 3. So 2p has a higher energy than 2s. Okay, we got that. We don't include the helium here. This is all valence. Let's see. I have 2 electrons on the 2s, so up, down. I have 2 electrons on the 2p, so up, up. It is Hund's rule, right? It's Hund's rule. Yeah, Hund's rule that says when you have degenerate same level orbitals, place 1 electron in each one before you go back and double. Okay, so this is our carbon right here, standard, and they have to tell you ahead of time what type of hybridization you're making. So based on the slide here we were doing, they didn't say this. Okay, it's here. They should have said this, people. Okay, they're telling you your hybridization should be sp3. Okay, so I see hybridization like a recipe, as in take the the S that you have available, and then use all 3 P's. That's how I see the sp3. Use the S and 3 of the P's. which is what? Oh, everything. Everything. Okay. Let me use a highlight here. So we're using all of these. We're going to mix these up. But since we're mixing them up, we're making, uh, I want to say scrambled eggs. I don't know. I'm thinking breakfast. We're mixing them up and making something like an orbital, a hybrid orbital where everything is mixed. So now they are all the same, right? Where you can't tell one from the other. So what you're making is brand new. So once you mix these, the hybrid orbitals are brand new and they are a mixture of these two. So the energy is somewhere in between. It's an intermediate. So I have one, two, three, four. You end up making four degenerate orbitals. Okay. Each of these degenerate orbitals now have a brand new name, not the name that was there before. These are neither S nor P. Now they're called the recipe's name. Each is called sp3, 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 sp3. Each new hybrid orbital that is now degenerate, matching the other new hybrid orbital, is called sp3. Okay, so the old standard ones stop existing. Now you have the new ones. Okay, so one, two, three, four, like we had here. And now the electrons we had, the four electrons, get redistributed in the new sublevel situation, right? The hybrid. So up, 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 up. Ah, so based on our carbon being sp3 hybridized, right? So we can say here this carbon is sp3 hybrid dies based on this and can, I shouldn't say can, is ready and is ready to form four bonds. Okay, based on the hybridization that this carbon did, it is ready to form four bonds. All you need is something to come in here with its unpaired electrons. It can place them here, 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 and here. And carbon is ready and has room for those four bonds to form. Okay, which it couldn't do in the situation where it was standard. So let me continue and show you this for the other type of hybridizations. Same scenario. Let me see if I just copy this. Trying to be a little lazy. It will make it a little easier if I can draw this and copy this over and over again. Copy. It's a little bit of a struggle for me to draw that all the time. Okay. Okay. So that was scenario one. Oops. That was scenario one. In scenario two, let's look at sp2 hybrid. Wait, what do they call this? Oh yeah, let's look at sp2 hybrid. How does this form? Now I know as far as the PowerPoint slide continues, they bring this in later on, but I just want to talk about the hybridization first before I bring in the additional layers. So I want to approach this differently, okay, than how the slides unfold the story. I want to stick with the hybridizations first. So let's look at sp2 hybrid. Remember, our goal is to create more room, right? So here the recipe is saying, take the S you have and then use two P's. Well, which two P's? And our goal is to create more room. Do we use this S, the one S we have, with these two P's? Or do I use the middle and the last one? Because it does make a difference, right? So I'll tell you this, since the goal is to create more room and spread and generate more unpaired electrons, the best combination will be to use the empty orbital as one of your orbitals of choice. So what I mean by that is, let me use a different color here, okay? Purple. I will use these two and then that one right there, okay? So the S and then those two P's. Since I use 1, 2, 3 here, then when I get my hybrid orbitals, let's see if I can join them in the middle. 3 boxes side by side. 1, 2, 3. These three are side by side because I mixed these three, right? These are my hybrid orbitals. But then this one here remains up here untouched. That wasn't part of my recipe, so it remains right here untouched. These three hybrid orbitals, oh, let me not forget, this untouched one is called 2p. Nothing happened to it. It didn't get hybridized, so it doesn't get a new name. It doesn't get put part of the three. Only those three got mixed together to make the hybrid orbitals, right? Okay, remember these have a new name. Their new name matches the hybridization recipe. These get called sp2, 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 right? That's what it took to make these hybrid orbitals. Okay, for the hybrid orbitals that got mixed, you see the number of electrons that were here in the mixture? 1, 2, 3. Okay, so I resort or redistribute the 3 electrons in these degenerate, right? I put one here, I put one here, I put one here. I have these degenerate orbitals right here. So 1, 1, 1. And this is sp2, a hybrid or hybridization. Okay, so, well, how is this top one different from that? You can see only 3 of the orbitals here were generated from hybridization. Now I have to go back and add, as I said, I'm unfolding things in layers. So I have to go back and add a certain concept. As we look at this here, I want to mention the hybrid orbitals. Hybrid orbitals can be used for sigma bonds and lone pair electrons. Okay, so as we start to see that, as we start to unfold even more mystery, I will point this out. Hybrid orbitals can be used for sigma bonds and lone pair electrons, as you say here only. Okay, so if you have a bonding situation where a sigma bond is required, that will be the case. Please notice sigma bonds are also viewed as single bonds, but sigma bonds are technically the first bond that's ever formed between 2 elements. So try not to be confusing in my illustration of what's going on. Sigma bonds are the first bonds ever between 2 elements. So let me see if I can write that here. I try to write things down because students tell me sometimes, can you write that down, please? And I know what they're doing. They're trying to slow me down. So let me write that here. Sigma bonds are the first bonds. It's really the first bonds, but first bonds formed between 2 elements. Okay? And I'm going to be not controversial, but I'm going to be a student and ask a question. Why don't you just call it a single bond? Why are you trying to complicate things, right? My teachers call the sigma bond a single bond. And this was just my own fault. So when it came to a double bond, I was confused about the single bond. I thought the sigma bond, I thought the double bond was 2 sigma bonds. And in the past, when I've tried to teach things the way I learned it, it was confusing. My students arrived at the same confusion that I had when I was a student. So I decided to say, okay, you know what? The sigma bond is the first bond because in the order of bond formation, sigma bonds are always made before pi bonds. So the order of the bond formation matters. You see what I'm saying? And then when I had those kind of questions in the exam or in the homework, I missed it because I didn't recognize sigma bonds were always formed first. That's why I say sigma bonds are first bonds, to help you with that if you ever run across that kind of question. Sigma bonds are the first bonds ever. Now, if a second bond is to form, the second bond will be a pi bond. If the third bond is to form, the third bond will be a pi bond. Okay? Sigma bond, first bond. As a pi bond, whatever, all those other ones, they are the other bonds that come after the sigma bond. I know we're learning so much. As I said, all of this, imagine learning all of this in organic chemistry if you haven't figured it out in general chemistry. It's usually a trip. But since we're covering here, when you get to organic chemistry, it doesn't have to be confusing, okay? So once again, let me try to summarize that. Number one, sigma bond, first bond, aka single bond, right? So let me say, for example, carbon combined with carbon, then the rest of this is hydrogen right here. This is called a sigma bond. Remember the symbol sigma? That's a sigma bond right there. Okay? Then we have pi bonds. Okay, so in this scenario here, I'm showing that the carbon bonded with the other carbon twice. So one of these was formed first, right? It in this order here doesn't really matter. We just assume one was formed. So pick which one. Let's say the top one was formed first. That top one will then be the sigma bond. Okay, then the second one will be the pi bond formed second, right? Formed first. Because remember, I told you guys it's the order in the bond formation matters. That's why if you just memorize this as a single bond, if you're able to memorize sigma bond as a single bond and understand all that, do that. Okay. I'm not telling you exactly how to learn it. I'm just showing you how I learned it. At that point, you get to repackage it in the way that makes sense to you. Okay. I'm not telling you this is the only way to learn this and da da da. No, repackage it in a way that makes sense to you. That's what I did, and the more I did that, the better I did in this course. Okay, so sigma bond, first bond. That means all these bonds here are sigma, 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 sigma. Because people who memorize this, they'll be like sigma, pi, sigma. I'm like, there's no need to guess. Do you see multiple bonds? Okay, so in that case, while we're here, why don't we define this? In that case, depending on how you choose to align them. If we have this scenario here, then let's say the middle one was the first bond, sigma bond. That means the second one will be a pi bond, and then the third one will be a pi bond. Okay? Just because all first bonds are sigma bonds, and then the ones that come later are pi bonds. Okay? I know. So, since these have unpaired electrons, all of these, in this case here, are sigma bond. Let's see. These they can form sigma bonds. So far, I don't see any lone pair electrons because if there was a lone pair electron, there'll be two electrons, right? So these are all, they're going to be future sigma bonds. Well, what about this? This one didn't make the cut. This here will be used to form a pi bond. That's why I went into all that dialogue, right? I hadn't forgotten. It wasn't like no, it was to say that this 2p that we didn't hybridize, that will be used to form a second bond. Okay, so pi bonds are formed by unhybridized p orbitals. When they say that later on, you're like, huh? If you read it before you see it, then it's like, what are they saying? I mean, if you ever say that, because I say that, I said to my husband, I'm like, you are using words and you think you're communicating. He gives me that look. That's what I say with the textbook authors. You're using words and you think you're communicating. I hear words, but I have no idea what you're saying. I hope you're not saying that about me right now. Anyway, let's go ahead and see how SP plays out. Okay, now we're going to be doing a hybrid. So I'm trying to go step by step so that y'all can see how, as we're going from one level to another, how it's translating. So in the end here, we're going to be doing just one S, one P. We're starting with our carbon. Once again, our regular standard carbon, take the only S available, mix it with the 1p. Of course, remember the goal is to make more space. So the best option will be this one, right? I'm not going to use different colors this time. I'm going to mix this one here and this. Okay. So after I mix these two boxes, I still end up with two boxes here. Two hybrid orbitals. Now, remember the hybridized orbitals have a different name. They're called sp, sp, after the recipe used to mix them up. And then I have these two unhybridized boxes up here. 2p, 2p, right? They're not part of the recipe. They didn't make it. This is kind of leftovers. Now for my two hybridized orbitals, I end up with, let's see, up, up, right? Because I have to put these two electrons in the hybridized orbitals right there. Okay, remember, these two here will be used for sigma bonds. This one up here, these two can be used for pi bonds. Okay, while we are here, two pi bonds, let's go back and try to tie this in. I know I'm doing this like, seriously? Yes, I am. Let's tie this back to what we just saw in the structures I was just drawing. So I know I wrote a lot, but since if you're watching this in video, you've already seen me. So I think it's okay for me to erase that, right? Let's go back to this carbon on carbon bond right here. This sp3 illustrates the bonding between these two carbons right here. These two carbons, let me highlight it, right? They are bonding this way. You can see that each carbon here is surrounded by 4 sigma bonds. So this is just showing you one of the two carbons, okay? So this is just one of the two carbons right there. It's showing you how it bonds. So you can label this sigma, 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 sigma. And then if they ask you hybridization, you write sp3, sp3, sp3. These are the orbitals that the carbon is using to bond, okay? Now here, once again, we are only showing one carbon. Oops, what have I done? Okay, here. Of the two carbons, we are only showing one of the carbons here, right? Only one of the carbons. Here, because we have one pi bond, this is showing you the carbon we are illustrating right here has a sigma bond and it has a pi bond, aka double bond, right? Okay, so I guess if I want to show you more of this, I can say this carbon here. Oh, sorry. Come on, Amber. Sorry, y'all. It's my Amber Alert. How do I silence this? Okay. Whew. This is all about the one carbon. Let's say my focus here is my left carbon. Okay. The left carbon is bonding with, so let me use a different color so I can show this. Let's say one of the hydrogens come here, right? That hydrogen. The other hydrogen comes here. And then it bonds with a carbon twice. So it bonds with the other carbon here and here. So this one carbon bonds twice. Isn't that what we're seeing over here? When you're looking at this carbon, it bonds over here one time, the sigma bond, over here the second time in the pi bond. So everything we're illustrating here is how this one carbon we are focusing on. I don't know why I'm leaning on the one carbon side like it's helping me. Okay, this one carbon we are focusing on is forming bonds with these other surrounding elements, right? And then as I'm continuing to illustrate the scenario here, let's go to triple bond. Carbon, 1, 2, 3, carbon, hydrogen, hydrogen. Okay, once again, this is illustrating the left carbon. Only the one carbon, right? Not both. Now you can apply this situation to both carbons because they're pretty much doing the same thing, just at different sides, right? So let's see how this bonding takes place. So this is saying here, let me use a different color again. The carbon on the left is bonding with a hydrogen. So I'll draw the hydrogen right here. That's this hydrogen here. But then this carbon bonds 3 times with the other carbon to its right. Okay, so this is the other carbon. It bonds over here, right? It bonds over here and over here. They must really like each other. They're bonding a lot right there. Okay. So that's why you can see that between our red carbon and then let's call this our blue carbon, the bonding is taking place 3 times. So one of these 3 bonds will be a sigma bond, the other 2 will be a pi bond. Okay. Imagine, right? Remember the days when bonding was simple? But why this complexity? Because this answers more questions about the observations that scientists were seeing in the lab. Now we're seeing why double bonds never form before single bonds, right? When we see why the pi bond never forms before the sigma bond, it does help if y'all see the shape. Okay, so now with the book, they do show you how. Now I was showing you how it went from sp3, sp2, sp. So now they're showing you sp3 hybridization. They're not just showing you the mixing of the 1s and the 3p orbitals. And use my red marker. I like that one better. It's a lot brighter. S and the 3p's, px, py, pz. This is just showing you the 1s combining with the 1p, the second p, and the third p, right, to form sp3, like that. So it's the 1s orbital you have, the 3p's next to it, right? And then this is showing you apparently there is some kind of intermediate here. And then once these 4 mix, they essentially form that. I know, guys, it is a lot of information. That's why I wanted to make sure that we had ample time to go over this. Okay. So here we're seeing, I guess the central atom here could be carbon. It could easily be carbon. Carbon ends up with 4 bubbles. So just kind of give you the simplest way of seeing this. When I see sp3 hybridization around a carbon, what I'm seeing is the S, the P, the P, the P. I am seeing 4 hybrid orbitals, right? Because it's a 4, right? 1s, 3p's, 4 hybrid orbitals. So what I'm seeing here is a carbon in the middle, and then the hybrid orbitals are drawn like bubbles or leaves, like that. Up, 1, 2, 3. Each of them is labeled sp3, 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 sp3. You don't have to go through like this intermediate part. Just know that these 3 form that. Okay. Now, of course, imagine this being 3D. I'm sorry, my drawing is horrible, y'all. This is, and I thought I was an artist when I was young. I was like, for real, I know how to draw. And my family said, yes, you do. You need to have your family tell you the truth. Later on, I entered the competition and they said, no, you're not good, sweetie. You are not good. Here, we're seeing sp3 hybridization play out. The atom with 4 electron groups around it. Geometry, because you have 4 electron groups, is tetrahedral geometry. Bond angle, 109.5 degrees, right? So once again, as we're going through this, what I like to do is look at my Lewis structure real quick. 1, 2, 3, 4. 4 electron groups. And then from this, they just kind of converted this into the hybrid orbital bubbles from the carbon, right? Each carbon is sp3, sp3, sp3. Okay, remember, hydrogen only has 1 electron. Hydrogen only uses the spherical orbital because it's always 1s. So in this section here, every time you see hydrogen, it will always be a circle. I was about to say it will always be blue. No, it won't always be blue. It will be whatever color the author picks. But hydrogen will always be a circle. Okay, doesn't hybridize. It only uses the 1s orbital. So hydrogen will always be a circle, S. And then in this case, carbon is using 4 hybrid orbitals. That means they're sp3. Okay. One way also to tell is sp3. This is, this is how I survived, y'all. When I was learning this, I wrote out the letters like this: S, P, 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 D, D. I was going to be using the letters from the left all the way to the right, depending on the number of hybrid orbitals provided. So I will use the letters as needed. So I named the first one S, second one P, third one P, fourth one P. Since I only had 4 groups around the central atom, that means these 4 groups were formed by consolidating sp3. Each of these was sp3. Okay. Once again, I know it's a lot of information, but that's why at least you guys have the PowerPoints to review and everything. But essentially, SPPP, that's if you have 4 groups. If you have 5 groups, SPPPD. You have 6 groups, SPPPDD. You have 2 groups, just the first 2, right? You're going from left to right and using the orbitals as you need them. Here, even in the structure of ammonia, right? So you should be able to work on some of your homework. This is the Lewis structure of ammonia right here. You count your number of electron groups. You have 1, 2, 3, 4. If you have 4, we're going with these 4. Well, that's not 4, that's 5. We're going with these 4, right? SPPP, SP3. So each of these is SP3. Even this one here is SP3, 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 coming from nitrogen. So the purples you're seeing here, each of these is labeled SP3, 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 because there are 4 groups. Remember, hydrogen, when it comes in with its orbitals to form a bond, same old, 1s, 1s, 1s. We don't expect any surprises from hydrogen. Very stable, very reliable, 1s. They showed you the sp2 hybridization. I already showed you guys that. With sp2 hybridization, once again, take 1s, 2 p's, mix it up, you get sp2 hybrid orbitals. It's going to be 3 bubbles or 3 electron groups. I told you about sigma bonds and pi bonds and how these form. Oh, one thing I didn't mention, sigma bonds are stronger than pi bonds. As I said, there's a lot of information in here. Even though there are fewer slides, there's a lot of information. Sigma bonds are stronger than pi bonds. And they're saying it has to do with the way the bonds lie, the orbitals lie, and how much of it interacts. Like when these orbitals are lying down, the overlap space is a lot bigger. So the bonds is a lot stronger. So if you're trying to pull these apart, you have to apply more energy to do that versus the ones that are doing it side by side. Okay, the side by side overlap. So here, hopefully you can see, of course, I do apologize. If you're like, this is what you've been drawing this whole time, I am ashamed. I know. Because let me tell you something, I'm not an artist, okay? This is my excuse and I'm sticking with this. Sigma bond, remember, this is the first bond that is, oops, what did I do? That's ever formed, sorry, that's ever formed between the 2 elements, whatever the 2 elements are. Okay, if they're using the p orbitals, that's the first bond ever formed, sigma bond, right here. This is usually head to head or end to end overlap. And then the pi bond forms second. So if you're seeing here, the pi bonds has to form above, over the sigma bond. So it kind of makes sense that this will form after that because it kind of forms here like that, above it, trying not to interfere with the sigma bond. Okay, so you can see how this works out. And they're showing you here half filled, and then of course full filled once the bond is formed. So like I said right here, the overlap between the hybrid orbitals occurs with the sigma bonds. The unhybridized are used to form pi bonds. So I've already explained all this stuff right here. So this is a picture here. What I'm going to do, I'm going to end today's lesson. I'll say start here for Wednesday. I want to draw the Lewis structure from this structure right here. Okay, I see that this carbon, based on the color, is using 3 hybridized orbitals, these 3. So the carbon on the left, oh, it says so right here, with 3 hybridized orbitals is sp2, right? Then I have an oxygen on the right where they haven't done anything to hybridize it because I guess it doesn't need to. The central atom is the one that's hybridizing, so it's carbon. Okay, so my Lewis structure, I have a carbon and I have an oxygen. Now it looks like I have two hydrogens, right? Hydrogen, hydrogen. Okay, this carbon uses hybridized orbitals to form a bond between carbon and the hydrogen, right? So this is one hybridized orbital, and then you have the hydrogen. Okay, so remember hybridized orbitals are used either for lone pairs or single bonds or sigma bonds. There. So this is the Lewis interpretation of what we're seeing here. But I'm going to add a little more. The carbon is using sp2 based on the number of hybridized orbitals. The hydrogen, of course, uses S, right? Just the one S. Okay. And then on the right, this is the first bond between the carbon and the oxygen. So there's at least one bond between these two, right? But then there's another bond that goes over the first bond. Oh, there's two bonds between these two. Y'all see that? Oh, it's hard to use the same color. Let me use black. This one here is the second bond between the carbon and the oxygen. So that will make one of these. The first one I drew, sigma. The second one I drew, pi. And of course, I can go in here and fill in the lone pairs on that. So I just use the structure on the left to do the structure on the right here. Remember, the hydrogen is using S. The bond between these two is sigma, the first bond. The carbon is using sp2 hybridized. Okay. And then they're showing here the pi bond, of course, was just from a regular 2p orbital. The sigma bond was from sp2. It is a lot. I do admit it is a lot. Okay. But go over this, work on some homework problems. The more you work it, the more you understand theoretically what's going on. But yeah. So I will start here on Wednesday, and then the rest of it will be well, I don't want to say it's going to be easy because that'll be a lie. We'll be more familiar. How about that? But this is all I have for today. Do you have any questions for me? Okay, if no questions, this is it. Have a nice day. If you think of anything, feel free to email me, okay? Okay, thank you. Bye.